So let's start. So welcome back to our AI course. So today we will look at games where we have an opponent, where we have an adversary, an enemy, if you will, basically somebody who does not have our best interests at heart, right? Previously, or previous lectures, we talked about search, solving some problem, but we sort of had our free. Nobody was basically attacking us. Nobody was trying to delay us. Nobody tried to put spikes in our wheels, so to say, right? So today we'll look at the games. Mostly we'll look at the two-player games because they are the easiest ones to reason about, right? So again, basically this is the topic of game theory, which is actually its own branch, actually. But of course, AI heavily overlaps with this domain or this topic. So there are a couple ways of thinking about your adversary, right? There's at least three ways of doing, right? Again, I think first of all you can think of pretty much any game or any situation, right? You have an adversary, right? Maybe they don't really hate you, right? Maybe they're just trying to they have their own goals in mind, right? So one way we could do of things, as the book mentions, you can think of it as all the adversaries just an economy of the world, state of the world. That's the way it is, basically, right? So it's not the approach we're going to look at right now. It's just like an aggregate approach. We have multiple adversaries, right? Also, another approach we could take is say, okay, there's an adversary, but it's just like rain. It's happening, right? But they're not really actively trying to influence us, basically, right? So, but the third one is where we model the adversary as well. So not only us, not only our agent, but the other agent. Of course, the other agent could be done by yourselves as well, right? There could be multiple agents acting, right? So we have what kind of environments? We have multiple, environments where we have adversaries. Of course, games is the one. Is the simplest one, right? You have specific rules, right? Specifically, zero-sum games. What's a zero-sum game? It says on this. You can read if you want, but you can give your own definition.
Well, one gains something and the other loses.
Yes, and what's a key part of the zero-sum?
There's only one winner?
Yeah, but it's basically this: you gain if you take $50 from somebody, right? If somebody robs you from $50, right? They gain $50 and you lose $50, right? Right? It's a zero-sum, classical zero-sum. So if you go gambling, right? Yeah, so yay, but it's it's a classical zero-sum game, right? You have potential to win, of course, casino, right? Or the other party, or the counterparty, right? Takes something away. So for example, let's look at poker, right? You play poker, you go to casino, right? Well, you're playing against, if there were no, what you call rake, I guess is the name, right? For the casino, right? The take. It would be a zero-sum game. Because you have only players, they put money in, you put money in, right? And, well, somebody wins, and of course, maybe there's multiple winners, but basically all the money goes in, all the money goes out. But of course, if there's a casino which takes a percentage, right? That's not really a zero-sum game. It's actually a negative game. I guess that's the name. But basically, it's a negative-sum game, basically, right? And of course, how about the economy in general, right? Is it a zero-sum game? Well, some people argue that, for every winner, there's a loser. But of course, if it's a growing economy, right? Rising tide lifts all boats, right? There could be multiple winners, meaning the output increases, right? $100 go in, and maybe $150 go out. Meaning the pie gets bigger, right, in the ideal world, right? So, again, but here for simplicity, we'll start by analyzing mostly zero-sum games. So there's a winner, there's a loser, right? So, again, as slowly we'll build into how to incorporate uncertainty and how do we incorporate strategy in our games, basically, right? So, adversarial search, right? So you have a competitive environment, right? And you have your opponents, right? So outcome does not depend just on you, right? So You need to find the goal, your optimal strategy that takes account of what your opponent is doing, right? Like again, if you're playing chess, right, you try to checkmate your opponent. Most likely, unless you're going for scholar's mate and the opponent you has just learned the rules of chess, right, it's not going to work, right? So your strategy might not work, right? You have to account for the other party, right? So how do we represent the games, right? How do we represent this strategy, right? We'll talk about minimax algorithm, right? One way to do this is to use something called game tree, right? One move, another move, we model, again, 3 types of structures to model the moves. Let's see if we can get to some games. Of course, again, chess, checkers, go, poker, right? But poker, of course, is not it could be a multiple player game, right? But let's see, I'll probably talk about tic-tac-toe, right? Dashes, right? But that's the easiest one to start with, right? How about physical games, right? Like hockey or football, right? Well, there used to be actually AI really tried to avoid them. There was actually robot soccer, right? Robot football. I think I had some pictures. Robot soccer, right? Kind of funny fails, right? Right. It used to be pretty bad, right? But actually, it's its own. There's RoboCop Federation, right? And you probably have seen the videos of them falling down, right? Yeah, it's pretty serious business, actually, right? But it's actually they gotten quite good, actually, of course, in later years, right? Basketball, I have not seen them. I'm sure somebody has tried a robot basketball. I don't know. Has anyone seen it actually?
Yes, there is one from China.
Yeah. What do they do? Try dunking or just?
It's just 3-point.
Just 3-point shooter.
Yeah.
Well, I would imagine that actually could be worse. That part seems easy, right? I mean, you just adjust, right? 3-point shooting, right? Hey, make some sort of actuator, right? The release mechanism, right? That might be worse, a project, I don't know, right? Interesting, right? But actually, real game, it would be kind of hard, right? Tennis, right? Of course, we have a different training. American football, of course, very hard, very physical, right? Volleyball, right? But again, so right now, most analysis of AI deals with, actually games which are actually, not so physical, right? So, RTS, right? Real-time strategy games. I think who plays real-time strategy games? Right, which ones? Okay, yeah. So, but the question now, civilization is not a real-time strategy, right? It's a turn-based strategy, right? I've spent way too much time playing civilization. Yeah. So, yeah. So, civilization is interesting.
What about Warhammer?
Warhammer, is it turn-based or is it real-time? Excuse me? Oh, I don't know. I mean, like I said, the question is there basically real time means if you're not doing something, stuff happens, right? You can lose if you're not doing anything, right? Turn-based civilization, like example, it's your turn. You go to outside, you take a break, you come back, right? You make your move, right? That's turn-based, right? Real-time strategy means if you go outside, you lose, right? Right. So that's one of the key factors. Yeah, like I said, I'm a big fan of StarCraft, of course. So this actually has been lots of bots for StarCraft and StarCraft 2. Actually, lots of research. They're still bad, actually. They're still bad, right? So there's something interesting things for most of these games. There's something called fog of war, right? Meaning you don't have the full information, right? So lots of different. There's some examples, right? So yeah, this is again. Like the next level once we get past the basic games. But let's look at the basics today, and let's look at our 2-player zero-sum game, and let's look at tic-tac-toe, right? And again, I'll probably use paint, right? And let's look at this idea. And again, I will draw, and I will use, since a book mentions, of course, we'll use classical tic-tac-toe, right? I will use some really stupid tic-tac-toe, 2x2 tic-tac-toe, right? Oops, oh, come on, right? So I think the first player who starts wins, right? All right. So but let's go with, okay. So it's really not a fair game, but How do we, okay, the reason I'm doing it because we, right? Right. Yeah, but let's model this game, right? So how usually is min max? How we so we will model first player. You know, let's call him X, right? X, right? Wins. We'll give him 10 points, right? Draw, right? Meaning will be 0, right? And you know, if 0 wins, X wins, right? Wins. 0 wins will be minus 10, right? I'll use arrows because to compare, so you can see the minus. So you again, it could be 9,000 or it could be 1, 0, minus 1, right? In this case, right? So where is this number important? Well, it becomes important when you try to model states. Maybe there's some uncertainty, maybe there are degrees of win, right? Maybe there's some cutoff points when we start pruning the situation, when we start evaluating the position, right? But right now it's very basic, basically. You know, 10, 0, minus 10, okay. So, basically you have game 3, and we can start like this. And I think I can do this all, right? So, well, actually, right? So, we have we put X here, right? Right? And then we have, well, 3 possible states, right? 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 And I will just model, because this is easy, right? Otherwise I'm doing it, right? So, right? So, in a full min-max algorithm, right, we will go towards when we can't go anymore, right? So this is actually going to be, is this actually a game? I see this is an interesting game. I don't think you cannot even draw this game with X, right? Right? It's impossible, right? Not a fun game, right? But okay. Okay, I'll leave it here, right? Because that's a given, right? But this is max, this is a max guy, right? And this is a min guy, right? The other guy, min 0x, right? So, 0, right? 0 and 0, right? All, right? And then we go on, right? 2 states. And this is really stupid again, right? So we have x 0, right? So I guess we could introduce a rule that no diagonals don't win, right? It's draw, so make it more interesting, right? I'll add, so this is already not fair for the 0 player, right? So yeah, we'll add, so we'll do this is right. This is win, right? Right? Win, so plus 10, right? Plus 10, right? And then this would be nothing, not terminal, right? Still game. And there's one move, right? To make things interesting, right? So x, 0, 0, draw. All right, you get the idea, right? So same thing goes here, right? So of course, again, I'm really lazy, right? So x, and I forget, right? So x, so this again will be win, right? Plus 10, right? Plus 10 win. And here we have x, 0, and again, so x, 0, 0, draw, right? Right, and same thing goes here. But of course here, it's impossible to even draw, right? Because the 0 player played really badly, right? Right, and you can't even draw, right? You can't, so you're forced to win, right? Right, plus 10, plus 10, plus 10, right? So I couldn't even get minus 10 here, right? As hard as I tried, right? But hopefully you trust me that we have covered all the possibilities if we start the X upper left corner. And again, I think here you can also very well argue, right, that since game is symmetrical here, rotations, you could basically same, we start with here, it doesn't really matter, all corners equally, right? So we have covered all the game boards, we can simulate. So we have how many, how deep is our tree, right? Up to 4 moves, right? 4 moves, 1, 2, 3, 4, right? We have to actually start, technically, we have to look at these two, right? Right, but we don't really, I'm not going to do it because, again, why should I, right? Right, since it's, right, so you see, okay. But yeah, so when the max, there's a max, so there's, if two-player game, you have a max step and min step, basically, right? So how do you determine how do you determine the optimal strategy, right? You have to go through in a full min-max algorithm, right? You have to go through the full step, right? So at each step, when it's max turn, right, it tries to maximize the value, right? But you have to consider that the guy who is playing the minimize, the other side, is going to try to act against it, right? So again, so this possibility, right? 0 would not pick this one, right? Because this has plus so no matter what happens, this ends up with +10, right? So this should not, in a rational player, if your opponent is not a random player, but that's another strategy actually, right? This should not be, this will not cover, right? I mean, maybe I'll make it, yeah, bad for min player, right? Because, this is really a horrible move, right? So, because he sees these are terminal, these are all terminal states. So these are terminal states, right? Right? These are all terminal. Meaning the game cannot proceed. We have the rules, right? So we have full state of the game, basically, right? This is also terminal, right? Terminal and terminal, right? So we have all, so basically you follow the tree until you reach the terminal state. So here, of course, again, you can see these are sort of, again, doesn't matter, which way you play, right? We can clearly see no matter what the minimum guy does, right? Max guy will actually reach the +10, right? Because he knows, okay, doesn't matter which one of these picks, right? The min guy can still hope, okay, maybe this guy does not know the rules and he will just, put here, right? And then you have a draw, right? Right? So, yeah. Because again, remember, for the first move, could be completely random, doesn't matter, right? It's only this part here is where it actually happens, right? So, but hopefully you see the idea of how we can simulate the full game tree, right? For the tic-tac-toe 2 version, 3x3 version, right? Book mentions 3x3. How about chess? Can we draw a full tree for chess game? No. No, you can tell, you can imagine, but it's about 10 to the 135, I believe, right? Which is based more on atoms and universe. The tree will be huge, right? So we will need something better than this, actually. So that's the problem, right? That's the problem. We will need something better. Yeah. We will need something better, right? Right. So optimal decision, max, like I mentioned, the guy who maximized, try to minimize, right? Another thing, the ply. So, ply is an important concept in game theory. Oh, where is my game theory book? So, ply is what? This is one ply. One ply, right? Typically, sometimes they use two, so it's half move basically. So, one ply, two ply is one full move, right? So, two ply, one full move. But it's a half move basically, right? Sometimes you see again in chess, or many, if you look at your AI, your bots playing, right, there is a ply, how many ply deep do we go? So here we go, 1, 2, 3 deep, three ply deep, like 3 moves deep basically here, right? Well, technically 4 because we start here, right? That's also a move, right? We have also technically here, start somewhere here. Can I make this? No, I can't. Can't we go down, right? So technically 4 ply, but yeah, that's full move. So 2 moves each side, right? So if you say chess game is 25 moves, right? That's 50 ply, right? So very simple concept. Now, so that's the definition. So min-max value of a node, right? That's the best score. Again, the best score, assuming both players are not idiots, right? Yeah. So that's the key part, right? So there's a min-max decision. I say min-max with mini-max. Okay, it should be technically called a mini-max, right? So So decision, right? Best possible outcome, maximize for max, minimize for min, right? So that's the basic. Oh, here's okay. We can see it here, right? So -7, right? You try to maximize. So you don't pick that. You pick this one, right? So it bubbles up, right? So at each step, right? Max, max, max. So here you try to let's see how do. Okay, you try to max. Yeah, but the min guy picks the minimum. You see, the min guy will pick -7. So these are terminals, right? In this game, which we don't know what the game is actually, right? Here you can see the terminal values, right? The max guy would like to get positive infinity, right? But the problem is, right? He cannot get to this, right? Assuming again the min player is not an idiot. At this step, right? The min player makes a choice. He takes -10 here. He makes this choice, right? And this is like really simple. There's all -10 because there's only one solution, right? So that's what I'm saying. This plus infinity is not reachable by the max player. Now, let's think about, if you think about it, is it sometimes, if you are a human player, you have some knowledge of this, right? And actually that's how it happens in real-time strategy, in real life games in general, right? Sometimes if you are very good, right, but you see that you're better than your player, but the game is basically heading towards a draw, right? What you can do is, right, you can set a trap, right? In some game, like in chess, for example. You set a trap, it's perfect game, it's perfect play, nothing will happen. Maybe you even lose. Maybe it's a bad trap. Actually, it's actually a suboptimal play. So sometimes it might make sense to play suboptimally, right? If the trio of variations, this possible choice is large, and you expect that this player is not going to be able to find it. Because again, a reminder that this mini-max will give you a perfect strategy, but for almost all games, it's not possible to look at all these trio variations, right? I think checkers, but even checkers, you cannot do it with a pure lookup. So you can do it for tic-tac-toe, no problem, right? But for most normal games, you cannot do it, basically, right? So here's the algorithm, right? So basically, best move, right? You keep going, you propagate up the values up the tree at each level. So here's the min step. So you take the min value here. You start at it's bottom up. It's a bubbling algorithm, right? You bubble up. So you generate the possible moves, right? Okay. So here, right? So min here gets the minimum value, right? So here min value 5, not 7, right? Here not plus you get 10, right? Here you get 5, right? So 10. But even here you still don't get, right? So when you maximize, right? You pick this one, right? But you don't get this far, right? Because the min guy gets -10. So here, you pick this one, right? Min gets the smallest, and here you get max again. Poor guy gets -7, and min again chooses the most negative value, right? So again, reminder, terminal states, that's where the game ends. There's a draw, win, maybe there's scoring function, like big win, like if you play like, I don't know, some card games like Atsite or Zole, right? Who plays Zole in Latvian? Anyone? No, I guess nobody plays. Bridge maybe, right? Somebody has played or any card. Well, any game you have scoring, right? Not just a win or lose, right? And so that's why those scores could apply, right? You win by 7, you win by 7 or 5, like in, I don't know, it could be in hockey, right, game, right? So it's all very good. Here's a pseudocode for the minimax algorithm, right? So it's, of course, what kind of algorithm is it? It is, if you think about it, this is a pseudocode, right? Look, what kind of algorithm is it? What kind of function is it? Well, it is recursive. It's recursive because you call it self, right? Because, I mean, you could write it without recursion, but then it would be a real pain. You have to keep track of all the levels, right? Here you just recursively call it, right? So either max or min, right? So you get the smallest one, right? Yeah, you get the best value, right? Max or min, right? So recursively, right. So now the question is, what do you do in a more games which are slightly more complex, right? Well, okay, first of all, okay, yeah. If you have multiplayer games, right, you have a vector of value, not just min and max. You have a different directions, right? Min and max is easy to emulate, but maybe if we have 5 players, right? They each have their goal. You have a vector of values, like maybe scores, right? That would be one way of doing it, right? It gets much more complex, right, for 2-player games. Because what else happens in multiplayer games? You get alliances, right? It's possible, right? 2 weak guys gang up on the strong guy, right? Right? It's only basic strategy, right? And that's much harder to model. It's possible, right? You can do that, right? But for now, at this moment, we're not going to focus on it, but it's something to consider, right? So that's more extra length, extra strategic depth, right? So, alpha beta pruning. So the first thing, so minimax. So this part here, which I explained to you, right? So this makes sense, right? We bubble up, right? We start here, right? So 0, right? This is 0, right? This is of course 0, right? 0, 0, right? Yeah, this is plus 10, right? I'm trying to see if I can come up with a game where the 0 guy could win theoretically. Is it possible? No. No way. In this game, no, this is a really bad game. Probably nobody plays it, right? Yeah. Right. So, okay, but so alpha beta pruning, I think we have time to get started. This is one of the key ideas, right? So, idea is that you maintain 2 values. I don't know if we can show it to you. I don't think I'll be able to draw it, right? For the alpha beta, right? So, do I have a graph? Oh yeah, I do have a graph. Okay, very good, right? So this is a very critical point. So basically, as we are going through our tree, right, we have huge tree, millions, maybe billions of, wide tree, right, running out of memory, right. We would like some way of getting rid of some, how should I say, useless or not useful branches, basically. We want to cut them, pruning, right? So we skip certain branches. And this is not a guaranteed process, right? But the idea is this. If we find some values in this branch which would not help, basically, right? It's already, we can cut off early, basically. We can prune early, basically, right? So maybe let's show the idea. Let's see if I can draw this idea on a paper, basically, right? So we have alpha and beta, right? So let's see if we can do this. It would be kind of hard, but I think I can do it. Now paint again. If not, I will do it after the break. Or maybe I don't have to draw this. I can maybe make this bigger, basically. Yeah, I think I'll do that because okay. So let's take a look at this. This is from the book, actually, right? So originally, right? Let's see if you can see this here, right? Maybe make it bigger. I'll make it bigger. Can I just download this? I can show it to you. Oh, I have it here. Okay, let's go to my GitHub. I have it somewhere. Images. Oh yeah, and chapter 5. Where's my chapter 5? Ah, here we go. Right, alphabet pruning. Oh yeah, that's better. Maybe open. Yeah, that's even better like this. Okay, yeah. So we have initially positive, negative, alpha negative infinity, beta positive infinity. So it's all the possible ranges, right? So what happens is this: we go down depth first, right? We explore the left side here, alpha beta, right? So we know the value here is maybe possibly negative infinity, right? But possibly 3, the maximum value is 3. So question is now, why is it 3. Now a question to you guys. What do you think? Why is it only 3? Why is the maximum value at this branch, right? This is the min guy, right? Well, the maximum value is possibly only 3. Why? We got this is a terminal state. This is, some game ends here, right? You get 3 score 3, right? Well, the thing is, no matter what happens here, right? No matter what scores, right? We know if you get like 500, right? It's like here, look at this step B, right? We see, okay, 12, right? Well, the B player, right? The min guy, right? He is not gonna pick this one, right? It stays at 3, right? Because this one is, you know, even if imagine if there's lots more stuff happening here, it's still 12, right? We will never pick it, right? Okay, so 12 and 8, it's, so here it's minimum 3 and maximum 3, okay, right? So now we have a state negative infinity and 2, right? Why? Because we got 2, right? Here, right? So here, right? So look at this, the step. Let's see, where am I? Oh, here I am, right? So no, or here, right? So I'm here. It's not fully done yet, right? So that's step D, right? Yeah, at most 2, right? So the thing is, here, okay, so yeah, this is the deal, right? So this is 2, right? Because think about it, this step here. We get 2, right? So because this minimizing guy, now he can always get minimum 2, right? If no matter what happens here, right? So we can stop here right now. So this is the magic of alpha beta pruning. We can stop here. Why? Think about it. Because this guy here knows there's 3 waiting for him, right? He's never, there's no need to keep checking this, right? Because this is for the minimizer, right? No matter what is here, it could be, it will never go over 2. It will never go over 2. Why? Because the minimizer will make sure, okay, 2, right? If there's 5,000, 3,000, you know, no matter what number, it can only go down. This top value can only go down, but it is less than here. So the A player, right? There's no point, he's never going to check, there's no need to check this, right, this line. This is complete dead end, right, for the A player. Because the B player, the smart, assuming again, both are not idiots. Again, assuming both are not idiots, right? So this is important. So this is the core idea of alpha beta pruning. We have like a couple minutes, so hopefully this makes sense now. I'll have to draw this for you guys. Do you see this? Why we can cut this off, right? No, not yet.
Oh, yeah, what we do with this, like, how we proceed.
Okay, so the idea, okay, so basic idea is this, that here, so what do we gain? Why is it important? Because we don't have to look at these. We can have maybe 5,000 branches here, right? We don't care about them anymore because they cannot help, right? Because what happens is no matter what they are, right? They cannot increase this top score, this 2, right? It can only go down. It can stay 2, it can go down, right? So here we have 3, right? So the A player is never going to check this, never going to pick this branch. So how about this part here, right? So here we have 14, right? So look here. For E, it's 14, right? Can we get rid of it? No, we cannot because it's 314 here, right? We don't know it's 3 plus infinity because this is not explored, right? At this stage, it's 3 to 14. That's a good one, right? You put 3, but we have possibly 14 here, right? We cannot cut this off. We have to, so notice here again, we get 5, we still have to explore it, and we get 2, okay, no need. So one takeaway from all of this that we saw is that order of our terminal states is important, right? If this was 2 here, we could also cut it off immediately, right? So if you could somehow have a way of looking at depending on your need, of maximum states or minimum states, likely minimum values or maximum values first, some way of exploring it, this makes a huge difference, right? So you will need something like a hint, you will need some heuristics, you need some rules, some guiding light to say, okay, this is a good sort of like, explore this one first, right? So the order matters here, right? So you see here, so here you can see this example, we had to go through all of this, right? We had to explore all of this because 14 was first, 5 was next, right? If 5 and 2 were reversed, we will have to look at 5. Okay, I hope this makes sense. If you're not all asleep, not all of you, right? Because I will make you do something. This is some I'll implement. Second homework will be something about implementing some sort of game. I have not decided yet which one yet, right? You can come up with ideas. Somebody mentioned Nardi, right? Bagamon maybe. That's gonna. Yeah, you have some idea for game. We'll figure this out in a week or so.
You can give us the choice between multiple games.
Yeah, maybe. Yeah. I'm not gonna make you chess. No, don't worry. I won't make you implement chess, right? That would be like a big project. Yeah. Monopoly, is it to me? Oh yeah, that's an awesome game. But I wonder what kind of strategy we could come up with, right? Professional one. Right. Okay. So let's take a break till we can finish early. No, let's see. 10 or 15 minutes break.
We can go without break.
To me?
We can go without break.
You can go without break? Oh, wow, okay. Are all okay with that? Or maybe, are you okay? I've done this before in previous years. We did the last lecture without break. Right? Okay, all right. So we'll finish early. We'll finish about 40 minutes. Okay, let me get some tea, get some energy. Yeah, no. So we saw that, no. All right, so we can continue. Recording is going on. Or is there a recording? No, it's still recording. Okay, that's good, right? All right, so move ordering, significant importance, right? So good move ordering, right? So also another thing is, right, again, in real life, you might want to do something called iterative deepening, meaning you search, but you keep increasing depth search, right? Again, because in real life, I like saying this, right? And I'll talk about this idea. Again, another drawing, right? So we start some game, right? Minus infinity plus infinity. I can't, right? So something like this, right? So you have some moves, right? So this is max guy, right? Alpha guy, and beta guy, right? So iterative deepening, right? We look at first level, right? One ply deep, right? But maybe we want to go somewhere. There's terminal state here, maybe terminal state here, right? That's a really good one for the min guy, right? So if you have some, because it's possible, right? Like in a chess game, right? You have a checkmate under 4 moves, next color's mate, right? But maybe you have a game which goes 50 moves deep, right? Some games can go like, maybe multiple games, right? Something like this, right? And keeps going, right? So finding an early terminal states. So again, this leads to this, it all, how do we find them? Well, you have the general idea, but you will need the game-specific hints or some way of finding them, basically, right? Based on what the game is, actually, right? So, heuristics, right? So, let's see what game this is. Yeah, right. So, an early exit, right? And this is so a killer move. So, idea of killer move that you can cut off. Basically, there's checkmate. I'm going to be using chess, right? There's a checkmate which cuts off right here in my. There's a killer move, right? And you have a cutoff here, right? Killer move, right? Killer move. Killer move, right? Right, stops, right? Maybe this one here. Of course, if this one here is a killer move, right? We possibly here another killer move, right? You can stop early, right? So So finding these, right, might be important. So another thing to consider is that in many games, you have something called transpositions. What's transposition? Meaning you have two different paths, you arrive at the same position, right? You play like, I don't know, check or chess, like you move, I'll give you a chess example, move like e pawn up, somebody plays, e5, you play d4. That's kind of a stupid example actually, but yeah. But again, position might be good, arrived starting with d4, right? And then black plays e5, which is a gambit, but then the white player is kind of stupid when he plays e4, right? So, but the same position, it's arrived by transposition. So, you can use something called transpositional tables to save maybe basically hashes of positions that you've seen this before, basically. No need to repeat yourself, right? You can use a hash table for that. Now, so basically, for these type of games, we have two type of strategies. Type A, this is Claude Shannon. Who was Claude Shannon? One of the early pioneers of computing, 1950s. Basically, let me show you his picture. Claude Shannon. Yeah, this guy here. So he died actually pretty recently, actually, right? Like the father of informational theory, basically, right? He did everything. Like one of the, mathematician, electrical engineer, computer scientist, cryptographer, so very influential. Now, so he in his description of games, he said two types of strategies. Again, it's just like it's a scale actually. But he said, okay, there's one way of doing it. Type A, brute force basically. You go as deep as possible, right? You explore as many paths as possible, right? Then hopefully you either reach terminal state or you have some evaluation function. One thing I didn't mention yet, right? How do we deal with the game trees which are maybe 200 long, right? Well, one way we can do is maybe it's not true. We can sort of fake it terminal state. We have an eval function. We say, okay, we can stop. Let's do something. I don't know what is this pink, or something, right? We can eval, fake terminal state. Basically, we say, okay, this is good, right? This is we give some score like plus 9,000, all right? Basically, we don't look. We just say, okay, we're not going to look here. I have some rules in place, like which say, okay, this is actually going to, give a certain score. It's not a 100% true thing, but it's kind of a way of stopping you early, basically, right? So there's two. So going back to Shannon's idea, so type A does not have these too many evals. It just goes as deep as possible. Type B is smarter, right? Does not look at so many positions, in your path, but tries to eval many more of them. So humans, which strategy do humans use? What do you think? With the human players in any game, basically. What do you think? Which strategy do humans use?
Simple.
But
No,
B. Think about it. Do you hold card? Are you doing random strategy?
in some games, yeah,
But
that's the reason I usually don't play because I lose.
But here's the thing. Okay. So we humans, right? We use B strategy basically. Why? Or evals, and basically when you acquire skill or you become good at some game or something, right? Your neural network basically inside you, right, sort of learns a good eval, right? But consciously, you don't really look at too many positions. You look at very few, right? Maybe 5, 10, 20, depends on the game, Even if you're playing cards or Monopoly, it doesn't matter, right? You can only look at so few, but you have what you call, in Russian you say choice, right? But in Latvian you call a feeling, in English feel, or a sort of, gut feeling, exactly. You get a gut feeling, right? And that comes from conscious practice for learning, right? Eventually you become good in pretty much any subject, right? Or any skill, right? So here the same too. So humans are really good at this. So we are bad at calculating in general. We are bad at brute force. we can do million positions. So historically, the thought was that B would be the one needed, right? But humans, like the AI for game playing, would be type B. But what happened, right? In chess world, in Garry Kasparov, Deep Blue in 1995, right? Was mostly type A. So computers have gotten really good at type A. So very interesting, right? So B. So heuristic alpha beta 3 search, right? So basically, we can use the same knowledge from before of this beta 3, but instead of actually having these values, right? Again, these values don't come from the actual terminal state. They come from what? Okay, from eval function, right? So, right, we have some eval function, right? We have some heuristics, right? Because why? Because it's impractical to search the full game, right? Millions of positions we can't, right? We want to, well, computer can, but maybe don't do billions, right? We can do billions now actually, but again, the more you can cut, the better, right? So the modern game playing software for most will use the alpha beta pruning together with some heuristics, right? Again, so where do the heuristics come from? That's a good question. Heuristics used to come mostly from human knowledge, sort of like from this gut feeling, from this learned, right, feeling. But the thing is, there's another aspect of this. How do we, what's very important for this evaluation function? Complexity. Because if you're checking multiple positions in a game state, right? You don't want to spend too much time on each eval, right? You want to make it quick like this. For example, again, I'll give you chess examples, right? Since I'm a bit of chess player myself, so you have a classical way for chess. Eval is something you learn maybe in the first lesson. Is what do you use? The value of chess pieces, right? You know, pawn is 1, bishop or knight is 3 points. Rook is 4.5 or 5, roughly, depending on who you ask for. And queen is 9. Well, of course, king is priceless, but still, right? Actually, but you give king 3 actually a value when it moves, actually. But it's, again, but of course, you don't take a king. But so, idea is you can count the pieces, right? It's really simple eval, right? But you can get pretty far. It's a good starting point, right? Later on, like modern chess software, of course, use much more advanced techniques, counts maybe double pawns, things like that. Maybe 2 bishops is better than a bishop and a knight, and there are lots of advanced heuristics, right? But they start with the basic piece values, right? So and they build on top of that. So, because constraints, right? You're always dealing with time constraints, right? So eval functions, like I mentioned here too, right? So pawn is 1, knight or bishop 3, right? So you can keep checking. Maybe I'll show some examples. So yeah, yeah. So there is something interesting in the book. Actually, I don't think I guess something called horizon effect. So this is something. If you are cutting off too early, right? The program, the AI agent cannot see the things that are really bad, right? So it's a really interesting limitation, right? It can start might think, okay, it's kind of like it does not see that things are too bad, and it can start making these delaying moves to delay the inevitable deaths, basically, right? So humans with a human eval function can see situation is really bad, but computer really, I would say, stupid agent might have this horizon effect and might not see that there's a problem. I wonder if I have an example for this. Unfortunately, the book has it. I don't have it here. I would like to add this horizon effect example. But again, most of you not chess players, so I'm not gonna show it to you right now. But I can show it maybe next time, right? So cutoff test, right? So when we need to apply some, how should I say, a test to determine whether should we look deeper, or we can say, okay, yeah, this is good enough. I don't need to go deeper already, right? when I can start already cut off this branch, or I already know this is a good tree, right? So another thing is, of course, is a technique is forward pruning. That basically means you say, okay, those things are really bad. There's no point of looking forward, actually, but we know those are bad moves. There's no point looking at this position in depth, right? So I wonder if I could do maybe I could do a chess position example, right? Stockfish, right? Stockfish is probably still the best program in the world as far as chess strength is. You know, much stronger than a chess grandmaster, actually, right? So what does it use? It uses a hybrid approach: pruning, aggressive pruning, very good eval function, right? All right, and dynamically adjust the strategies depending on the position, right? So, yeah. Again, there's another technique we can use, right? Basically, again, those who took in my algorithms course, one of the core ideas is we trade space, memory for time, right? Again, I'll give you an example of chess. We can compute the endgames, and you have only a few pieces on the board, right? We can compute these. We know solutions. We can only get the answers. So what we do is we look up the moves already, right? We don't have to look into the on a game board. We don't have to do it again. We store the results basically. We can do it at the end. We can also do it at the beginning, right? We can do opening games, like how to open up, right? You can say, okay, these moves are stupid. Don't do those. Do the specific moves, right? And the responses as well, right? So, again, I'll give you an example of chess. You store various endgame positions, right? So, and the thing is now, once you know, you have these tables, right? You can perform something called retrograde analysis, right? You know certain positions, scores of certain positions, and you can work towards those, basically, right? So, you have maybe 9 pieces on a board, but you know the answers to 7-piece endgames, all of them, right? And you can use that. You have the cutoff points. You have the early cutoff. Basically, you have, okay, killer move. You have actually eval here, right? You have eval here from the table base, right? So again, so it's a balance. Right, we cannot store all the games in the world in a database, right? Because again, it's not possible, right? So we have to use search, but we also, if possible, some critical things we can look up, right? It's always trade-off, right? Time versus space. Now, so both search and lookup is in AI, of course, right? So what else? What else? Tree of variations is huge. There is another approach, actually. There's another approach. 1 second. What's happening? Why am I losing money? No, wow, okay. No, nothing. Okay. No, okay. So Monte Carlo. Monte Carlo. What's Monte Carlo? What's Monte Carlo known for? Book Monte Carlo? Monte Cristo. Casinos, yes. Of course, there's also Formula 1 F1 racing, but Monte Carlo is very tiny, basically. Monte Carlo, right? Right. It is in French Riviera, right? It's actually, it's not Monaco, it's Monte Carlo, right? So famous for casinos. No, it is from Monaco, yeah. It is a administrative area of Monaco, right? So very tiny place, but probably one of the most expensive places in the world, right? Only 15,000 people are citizens, right? So pretty nice weather, right? Right now it's like 12 degrees. Nah, that's okay, right? Very exclusive, right? Pretty much all, I mean, these are just few movies, probably James Bond movies, few of them, right? But yeah, but why is it important to us? Because Monte Carlo to basically casino-like approach or random approach. So again, randomness has its place. We can use a random approach to simulate some games, basically, right? So when you have a huge tree, right, your tree of variations is huge, we can use randomness to explore. And that seems like, okay, what a weird idea, right? Just do some randomness, pick something, right? So what we can do is we can sort of play a game, basically, at random, basically, right? Or use some really light strategy, right? And then we can simulate some games, right? So pure Monte Carlo is basically just a completely random, right? You don't build a search tree, right? So idea is this, you sort of play random games, right? And see which one is better, right? So it's kind of like statistical approach, right? Obviously, you can. What's the disadvantage of Monte Carlo search is you will miss some situations, right? I mean, by definition, you just randomly picking some states, right? Statistically, right? But you will miss something, right? It's simple, right? But it lacks the depth. So you might want, again, some hints. You combine it with regular exploration, right? Moves, you have some hints where to throw the dice, right? Don't just throw dice blindly, but you throw dice into certain direction, basically, right? So you expand the tree of variations, basically, right? And basically, you come up with a probabilistic model, meaning you have, okay, this is pretty good branch to take. This is pretty good area to go and explore more, right? So, of course, again, you need some formula, right? Maybe also you use an eval function. You don't play the full game, but you actually stop early. You say, okay, this is good enough position, right? This can save time. So, later on, when we start talking about machine learning and reinforcement learning, right? We can use that Monte Carlo to learn something about the game state, right? And these simulations can guide our strategy, right? Extremely powerful idea. It applies actually to, I think, AlphaGo. I think AlphaGo was, I believe AlphaGo used this approach, if I remember correctly, to learn. Monte. Oh, here, let me turn on. Come on. Oh. Enable. Oh, yeah. Monte Carlo search. I think AlphaGo did it. I think. Maybe I'm wrong. Yeah, it is. Right. More. Yeah. Let me see. Is this the link? Oh no. I don't need this exclaim. Let's check if this is correct. Oh yeah. These guys are like the heavyweights of AI. Denis Hassabis. He has his own startup, like multi-billion startup. Now, of course, he went from left Google, right? But basically, they did what was thought impossible. They built a AI agent, a game player, which beat the world champion in Go, right? Who has played Go? Anyone? You have 19 by 19 board, right? But the game, chess was already beaten, game of Go, not programming language, but just Go, a game, ancient game, really simple, right? But extremely complex. Yeah, it can be both things at once, right? Something like this, right? You've probably seen it somewhere, right? So, Japan, Asia in general, right? Very old, older than chess. So basically, you put stones, you try to take the space and sort of like eat the opponent, right? Like something like this, right? You put the stone here and you eat the black. The black guy loses to the white guy here in this example, right? Or maybe the black guy wins against if he takes over. So there's strategies of these both sides, right? So both black and white sides keep fighting against each other, basically, right? So here is you can see also a balance, right? You put the stone here, white stone here, the black stone loses. If you put the black stone here, white side loses, right? So again, The reason it was thought to be so much harder because the branching factor, the tree of variations, right here, was much larger, right? This one here. So, but interesting enough, yeah, AlphaGo basically used this. Beat the world champion. I think he was Korean, I believe, right? A big milestone here, right? Showcased the power of Monte Carlo's tree search, basically. Let me see again if this link is good. Link is good. Where is my AlphaGo article? Oh yeah, here. Right, did I mention Monte Carlo? Right. So what they did is they used some reinforcement learning, right? So AlphaGo Zero had no knowledge. So it played games against itself, right? It's like tabula rasa, blank mind. It's like you learn math or learn anything. Instead of looking at books, you only know the rules. It kept playing games against itself, right? It's like if you were on a, I don't know, in a prison or in a desert island, right, or somewhere, right, and you don't have any teachers. You only have the game book, and you play against yourself forever, right? And eventually you learn. So this is like 40 days. After 40 days, AlphaGo was good enough. But again, in order to do that, of course, you had to have used something called reinforcement learning, right? But the games, of course, started out randomly, right? So, very interesting, right? Very interesting. Again, we'll talk more about the reinforcement learning in about a couple of weeks, well, quite a few weeks. Now, what else? We're almost done, right? You guys are very good sports. So, stochastic games. And what do I mean by that? This means it's a game where you have some randomness. And so again, backgammon is a prime example. All right, apparently there's a backgammon table in your student lobby, right? You're playing it, right? So you throw dice, right? So it is a game of strategy, right? But there's also randomness, right? So it's stochastic. You need strategy, right? So a completely random player, right, will lose. Because why do you have strategy, right? You have a decision what to do. By the definition, also Monopoly is technically a stochastic game. If you go, because why? You have a choice to buy a property or not to buy a property, right? Of course, you should always buy a property, but still. Also, you have some trades. You have some choices what to do. You also have choice. Do I want to leave jail or not leave jail, right? In Monopoly, right? It's an important part of strategy, actually, right? In the beginning, you want to leave the jail. Later on in the game, you want to sit in jail as long as possible, right? Right? You want the other guys to jump put on your hotels, right? You put hotels, you sit in jail, right? If possible, right? So, okay. Now, of course that complicates things because you don't have a full scores. You have only randomness, right? Because dice affects. You only have expected value. You don't have full value, right? So you can still use the ideas from Minimax, the thing we learned earlier, right? But harder. So the eval function, again, you have to take in account the probabilistic value, probabilistic nature, right? Challenges. Now we lead to partially observable games. So most real-time strategy games are partially observable, right? You start a game, you don't know what opponent is doing. Pretty much, but let's look at some other games which are partially observable. Well, card games, right? Right? You don't know what the opponent has, right? Only later on you find out what he have, right? It's partially observable, right? You have a fog of war, basically, right? You do something, and well. So again, do you need randomness? Yeah, you can have, of course, randomness as well, right? But the key idea is that you do not have complete information. Does this mean you cannot use it? Right. So poker, right? Pretty much most games, right? So how do you deal with that? Well, you use probabilistic models. You think maybe he has an ace, maybe he has a king if you're playing poker, right? You make probabilities, you make guesses, right? Based on those guesses, you have not only guesses, but you have probability, estimates, of the value, right? EV, right? Estimated value, right? So again, you can use that to model the strategies, right? It's just your tree will be, the trees I drew, right, will be much harder to model this, right? You say 70% chance, right? So you can model this, right? So unique strategy. It's kind of interesting that there is something called Kriegspiel, right? It's a chess, but you don't see other players' pieces. It's kind of weird. I never played it actually. I mean, I play a lot of chess, but I don't play Kriegspiel, but it's very interesting. So you have like a judge, or you have like a what do you call oracle, basically oracle or a god, right, which tells you what happens, basically, right? So very good for computer chess, right? So you need to ask, you need to tell if you do something, you get some feedback. Either nothing happens, you mean move the piece, or it's a legal move. Maybe you take some piece, or maybe you give a check or checkmate to your opponent, right? So using those like sensors, right, you can get some feedback and you can actually play this game. It seems weird, right? I never tried it. It would be interesting to try, right? So it's very challenging because to get a checkmate, right? But it's possible, right? So card games. Again, we talked about this. Poker, right, has also, of course, the human element, right? Bluffing is very important, right? In poker, not only you don't have full information, you also have this human element of bluffing. So this has been historically very hard to learn for the computer to learn, computer agents to learn how to bluff, right? It's easy to do estimates of probabilities, piece of cake, right? You know, 2 aces, 2 kings, right? But how much should you bet? That's been really, until recently, the best human poker players actually were better than the computer players. From what I understand, lately, the bluffing has also been not, I wouldn't say solved problem, right? But one of the key ideas is to be a little bit random, right? You don't want to be too predictable, right? If you only bet big if you have 2 aces, right, everybody will know that, right? If you are what you call loose player and a tight player, right? Who plays poker here? No one? Good for you guys. Yeah, good for you. Sometimes, yeah. So, yeah. Not for money, don't do that, no. For fun, for whiskey or something, I don't know. Right, so, yeah, so Librantos, I think, there's some games that actually, some latest programs have been able to get near human, performance. So what are the limitations of all of this, right? So, alpha beta is how well you have a heuristic, right, for your score, right, and also the order, right. Monte Carlo search, again, how far, again, you want to skip some moves, again, you need some way of selection, right. So node expansion, similarity, like which nodes, which ones do you expand, right, not here, but here, right, where do you go, like, again, expansion, idea of where do you expand, right, will depend on some sort of utility function, eval function, right. So, what else? So again, so it will lead, of course, this will all lead to machine learning, because this means that we learn from experience, your algorithm. Right now, oftentimes, the basic game playing algorithms don't learn, so you can say kind of stupid, you can say, right? They have good strategy, but they don't learn. Eventually, they want to learn, right? So, what have we learned today? We learned the basics of game theory, right? Talk about zero-sum games. Not all games are zero-sum, but we saw the basic zero-sum games, right? Adversarial search, right? You keep switching between minimizer and maximizer, right? In 2-player games, right? We saw the minimax algorithm, right? We saw the alpha beta pruning, right? So some other days of evaluation, right? So evaluation, you use something specific about the game, right? Something that's known about the game, like again for chess, the big pieces. For poker, again, you can see that maybe you have again, let's say if you want to make a move in poker, you want some sort of strategy eval, right? You could say maybe you will maybe have a database of players, basically how they play usually, right? That would be one way, right? Maybe are they loose players or tight players, for example, right? So we saw about Monte Carlo's research, and we saw also the partially observable and stochastic games, right? And again, it's a huge field, right? It's interesting enough, like like something like StarCraft. There is also competition StarCraft 2 playing bot, right? Let me see. StarCraft 2. There is a pro bots, I believe. There's a competition, right? They're not very good yet. I mean, they're good, but they are kind of bad still, right? So for most of these type of games, there's so many, because why is it bad? Because there's lots of these weird actions that humans figure out, and these little glitches, like StarCraft, the top players, like you put a hidden unit, right, and for some reason, the computer player did not pick up there's a hidden unit, right? It seems like there should pick up on this, right? But the hidden unit was put in maybe later than expected, for example. There are all kinds of glitches that humans find out, right, and exploit, right? Computers take a longer time to learn, right? So, yeah, because I saw it's actually the top bots, they're still kind of, I would say, kind of bad. They're kind of bad still, right? So, how about backgammon bots? Let's say backgammon bot. Probably pretty good, right? Come, oh, that's kind of cool, right? Reinforcement learning, right? Learns, probably pretty good, right? It should be pretty good because 42, but that's not very good win rate. That's kind of bad. But it's backgammon's kind of a relatively easy game to learn, right? So, yeah. Oh, I guess 70%, that's kind of good, right? If I don't know, you want to check. So, think about think about what kind of games you would like to build, right? So for assignment, I'll consider them, right? Also, we didn't really talk much about multiplayer games, right? Meaning more than 2 players, right? So again, poker would be one example, but other multiplayer games we know. Like I'm talking about table-based games, like something you. Which one?
Game of Catan.
Which one?
Game of Catan.
Oh yeah, of course, yeah. That's certainly, and again, I think if I remember correctly, Catan does have alliances, right? Not really?
Not really.
Not really. No. Yeah. I'm thinking of Saboteurs. Saboteurs is fun, right? You play Saboteurs? Yeah. It's a good game, yeah. Right. So, and so, good one to try. All right, I guess we went through all of it right now. So next lecture will be on constraint satisfaction problems, which is kind of something we cover in algorithms. So that's going to be easy for those who are taking algorithms, but it'll be good. But it'll be good for those who are not taking algorithms, right? So that will be next on Thursday. So I guess we are finished today, right? Yeah. All right. Any questions? No. That will be next week. This one here.